Okay, so today I want to do go over some of the homework with you guys. Not the whole problems that I assigned in the assignment for this week, but I'm going to do something similar to those and go over some of the homework problems from sections 5.1 and 5.2. So hopefully, 5.3. So hopefully that will get you guys in a better shape and more comfortable with the homework. So for example, if you look at number, say in 5.1, you see a lot of tables and charts in the first part, the same way like in Math 1A, you saw a lot of tables and graphs that Stuart uses to make you guys visualize what's going on a little bit better. So you won't probably see those on the test, but or not at the extent that Stuart uses it, but still it's not a bad idea for you guys to be familiarized with it as you do the homework. So for example, problem number 2, if he says use 6 rectangles to find the estimated each type of the area under the given graph from x equal to 0 to x equal to 12. It says L6, which means you're going to use the left endpoints with 6 partitioning. And then R6 means use the sample points for right endpoints with 6 partition. M6 means use the middle point for each one of them. So if I use, again, I'm using 6 partitions. So that's one partition, that's another one, that's another one, and that's another one, and that's another one. So I get the 6 partition that I have. So 1, 2, 3, 4, 5, and 6. Okay. And then if I'm using the left endpoint, then that means for the first partition here, I use the value that happens at the left part. So it's going to be 8, and this is going to be my rectangle. If I'm at the second one, I'm going to use this part. So it's going to be slightly less than 8. And I get this one. If I'm at the third one, I use a left endpoint again. So it's going to be slightly more than 8 here. But that was actually 9. Sorry. First one is 9. And then for the fourth one, I get slightly over than 7. For the fifth one, I'm going to get a value that's about 6. For the sixth one, if I use a left endpoint, it would be a value that is about 4. So left endpoint means I use this one, I use this one, this for this, this for this, this for this. So the value at each one of those heights. Okay. If it was a right endpoint, then for this one, I will be using the right value, go backwards, 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 and create the area under each of, or a valid area underneath of each of those graphs. Okay. And then M6 will be using the middle value for each one. 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 So if I go to my screen here, what I have is a decreasing function that looks like this. I have values up to 12, 2, 4, 6, 8, 10. And let's say 12 is here actually. So 2, 4, 6, 10, 12. And then that's how I get the partitioning, the 6 partitions. And then, as I said, once again, if I do the left endpoint, this will be the left endpoint. And if I do the right endpoint, this will be the right endpoint. Midpoint, then you look at the value at 1, a value at 3, value at 5, 7, 9, 11. So those will be the values you would use. So here you're going to flatten it at that level. Here you're going to flatten at that level. Here you're going to flatten it at that level. Here you're going to flatten at that level. Midpoint, of course, you're going to see later we're talking about is the best approximation among the 3. So for example, if I were to do the left endpoint, then I would do left endpoint would be f of 0 plus f of 2 plus f of 4 plus f of 6 plus f of 8 plus f of 10, 6 partitions again, times 2 units per width of each of those rectangles. If I do R6, then it's going to be f of 2, f of 4, f of 6, f of 8, f of 10, f of 12 times 2. You have to eyeball these values. You cannot. And if I do midpoint 6, it would be f of 1, f of 3, f of 5, f of 7, f of 9, and f of 11. Again, eyeball what those numbers are, times 2, again, the width of the interval. So that's how you do problem number 2. And then part B of it says, is L6 underestimation or overestimation for the true area? So think about that. If I use left endpoints, do I get more than the true area or do I get less than the true area? Is it an overestimation or is it an underestimation? Overestimation means you actually think it's more than what it really is. Underestimation means you actually calculate it to be less than what it really is. And some question goes for R6, which of the numbers L6, R6, or M6 gives the best estimate? And that's really just based on your approximation. But as I told you guys, M6 gives you the best approximations for these problems. And then you get to the next problems that ask you, actually, they don't give you a graph, like number 3, 4, and 3, 4, 5. That would actually give you a function and then give you some interval over the function, and you have to partition it into pieces and then do the things from left endpoint, right endpoint, midpoint, and see how they compare, so forth. So like if you say problem number 5, the function is 1 plus x squared, and then they say between -1 and 2, use 3 rectangles. So -1 to 0, 0 to 1, 1 to 2. They usually make the interval to be very nice. And so use 3 intervals, 0, 1, 1, 2, 2, -1, 0, 0, 1, 1, and 2. And then you calculate the area under those using left endpoint, right endpoint, and midpoint. So let's actually look at that one. So for number 5, I have a function x squared plus 1. So it's a parabola. I'm not going to do the whole thing. -1 is here, 1 is here, and 2 is here. Again, it will be at 4 level. So this is 1, this is 4. My graph is not to this scale, obviously. And these are the 3 intervals. If I use the left endpoint, I will use this as my height of the first interval, this as my height of the second interval, and this as the height of the third interval. So L3 would be f of -1 plus f of 0 plus f of 1 times 1. F of -1 is -1 squared. F of 0 is 0 squared. F of 1, 1 squared times 1, which is going to be 2. If I do the right endpoint, 3, now I will use this as my approximation, this as my approximation, and this as my approximation. It's going to be f of 0 plus f of 1 plus f of 2 times 1. F of 0 is 0 squared, f of 1 is 1 squared, f of 2 is 2 squared times 1, which is going to be 5. If I did the midpoint for this, then I would use the value at 0.5, -0.5, +0.5, and 1.5. M3 would be f of -0.5 plus f of 0.5 plus f of 1.5 times 1, which is going to be 0.5 negative squared plus 0.5 positive squared plus 1.5 squared times 1, which is going to be 0.25 plus 0.25 plus 1.25 times 1, which is 1.75. Now today's lecture, you remember if you watch if you're watching the lecture sequentially, then we discussed the integral can be calculated exactly. So the integral from -1 to 2 of x squared plus, oh, this is, I'm just doing x squared, sorry, it's supposed to be x squared plus 1. So yeah, plus 1, plus 1, plus 1. So it's going to be 2 plus 2 is 4. Once again, this is plus 1 plus 1 plus 1. So you get plus 3 is 8. And this one is going to be plus 1 plus 1 because it's x squared plus 1 again. So it's going to be 1.25, 0.25, 2. So you get 4.7. So if I integrate x squared plus 1 dx from -1 to 2 is 1/3 x cubed. That's based on today's lecture. This is the antiderivative of x squared plus 1, and evaluate from -1 to 2 is going to be 1/3 2 cubed plus 2 minus 1/3 -1 cubed minus 1. So it's going to be 8/3 plus 2 minus 1/3 plus 1. So it's going to be 9/3, 7/3 plus 3, which is going to be 16/3, which is approximately 5.33. So 5.33 seems like the best approximation really is the midpoint approximation, which is what was expected anyways. Yeah. Okay. It's good to have more tools to use for other problems. So using fundamental theorem calculus to solving this was actually helped me catch my error at the earlier part. As you go through the problems, you see that again, now he's introduces, like problem number 13, he introduces tables. And now you're talking about times and velocity, trying to calculate the distance. So, so like in number 13, you see, it says that the speed of a runner increases steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table. Find lower and upper estimate for the distance that she traveled during these 3 seconds. So again, you have now, and you're just going to be using all of the values. It doesn't say how many intervals, so just use what you have. So if I have at 0, I have 0 at, sorry, at 0, I have 0 at 0.5 is going 6.2 feet per second. At 1 is going 10.8 feet per second. All the way at 3 seconds is going 20.2 feet per second. So if I wanted to use left endpoint approximation, I would use this, and this for my left endpoint. For right endpoint, I would use this, and this for my right endpoint approximation. It's steadily increasing. So again, it goes back to the problem we had, which one is overestimation, which one is underestimation. So if it's increasing, if I use the right endpoint, I'm going to get more values, higher values each time. So right endpoint would give me the upper estimate. Left endpoint, on the other hand, would give me a lower estimate. So for this problem, if I were to do this, problem by sketching a graph that would kind of resemble the idea here. So at 0, I have 0. Sorry. At 0 is 0. At 0.5 seconds, it's 6.2. At 1 second is at 10.8. At 1.5 seconds is 14.9. At 2 seconds is 18.1. It's not linear, obviously. At 2.5 is 19.4. And at 30 seconds is 20.2. So if I do think about it as a graph and say, okay, I want to calculate the distance traveled, right? Then I could just sketch the graph that we're going. And again, don't think about any specific graph or anything. It's just some function that goes through those. And I'm just approximating it. If I use the left endpoint, the area would be this. And the area represents the distance traveled because you're multiplying the speed times the time, speed times the time, speed times the times. The area of the rectangles gives you the distance traveled, and then you add them together. So if I use the blue, I get a least value of the total distance traveled. And that would be 0 times 0 plus 6.2, sorry, 0 times 0.5 plus 6.2 times 0.5, that would be the second rectangle, plus 10.8 times 0.5, plus 14.9 times 0.5, plus 18.1 times 0.5. And finally, the last one before times 19.4 times 0.5. That would give me a lower estimation. The higher estimation, the upper bound would be if I use the right endpoint approximation. And I'll let you guys do that one. So that's a purpose. Again, remember, if you calculate the area below the velocity curve, you're actually getting the total distance traveled. And then it asks some questions about in problems number 21 through 23. It says use definition 2 to define an expression for the area under the graph of f as a limit. Do not evaluate the limit. So it basically says write the limit of the Riemann sum without actually evaluating the limit. So say number 20, I think 21 is what I assigned, but like say number 22, your f of x is x squared plus 1 square root of 1 plus 2x. So I want to write a limit of the Riemann sum that would evaluate that. So for f of x is x squared plus root 1 plus 2x, and your x is between 4 and 7. So delta x is going to be 7 minus 4 divided by n, which is 3 over n from the before. And your area would be approximately, or actually I'm going to write the limit, so it's going to be exactly limit as n goes to infinity, if the limit exists, which in this case it will. Limit as n goes to infinity of sum I equal to 1 to n f of xi star delta x, which is going to be limit as n goes to infinity of sum I equal to 1 to n. It doesn't say use right endpoint and left endpoint. So you're really not expected to write xi's, what xi's represent. You're just supposed to write what the Riemann sum would look like for this. And you can use xi star as your representative x in each interval. So you could do it that way. Or if you wanted to just write out, say, left endpoint or right endpoint in either case, you can write that out and go that way. Now on the definition 2 that they're referring to, it's uses the right endpoint approximation. So, but again, as I said, you can write it, or you can just write it as they fall after that with the xi star and y star and delta x. So xi star would be what you would use for x in both cases, plus square root of 2 plus 2xi, 1 plus 2xi star. Delta x is 3 over n. Now, if you want to actually write out using a right endpoint, you could write it as limit as n goes to infinity, sum I equal to 1 to n. For xi star, it will be right endpoint, so it will be the 4 plus I delta x, which is going to be 4 plus 3i over n. So it's going to be 4 plus 3i over n squared plus square root of 1 plus 2, 4 plus 3i over n times 3 over n. So you replace it with the right endpoint corresponding. Again, if I say just write the limit of the Riemann sum, all I want is just this, or you can just even leave this as delta x, just tell me what delta x is. But if I say use Rn to calculate the area or approximate the area, then you will have to write this. So they refer to its definition 2, which actually uses the right endpoints for this one. 24 and 25 take the reverse form than 21 through 23. They give you limits of the Riemann sum, and they ask you to write out what the function would have to be, or what's the area that is determined by this limit of the Riemann sum. So on 25, for example, you have a limit as n goes to infinity of sum I equal to 1 to n of pi over 4n, tan I pi over n, 4n. So pi over 4n will be representing your delta x, which is b minus a over n, is pi over 4n. So the length is b minus a would have to be pi over 4. This guy is supposed to be your a plus I delta x. And I know my delta x is pi over 4n. So that takes care of this part. I is I, so which means my a would have to be 0. So if a is 0, b minus 0 is pi over 4, which means b is 4. Pi over 4, sorry. So my integral is from 0 to pi over 4, a to b, and the function is 10. So what kind of an area does it represent? The area is a function, the area underneath of a tan graph. This is pi over 2, the asymptote, from 1 to pi over 4. From 0 to pi over 4. Sorry. So that's how you would approach that problem. Okay. Yeah, there are a lot of nice problems in this section, but again, as I said, I'm just highlighting some of the important ones for you guys to get comfortable with for the homework if you're having some tough time with some of those problems. Okay. So when you go to section 5.2, they ask you on I hope you guys see okay here. Let me stop sharing. First few problems, again, it goes back to the concept of Riemann sum and the area under the curve, and it tells you the number of partitions. So if you look at like number problem number 3, it says if fx is x squared minus 4, x is between 0 and 3, find the Riemann sum with n equal to 6, taking the sample points to be midpoints. So you're talking about the midpoint calculus. Same thing we did in the past, but now you're using a different function, different interval, and halfway in between each interval as your sample points. So that's, again, something that is very similar to what we did, but with the new language of Riemann sum and calculating the area and so forth. Then it gives you an actual function, actual graph, not the function, actual graph, and it says calculate the integral from 0 to 10 of f of x, and use right endpoint, left endpoint, midpoint, and you're using 5 subintervals. So if you're doing this problem with 5 subintervals, then that will be 1 subinterval, 2, 3, 4, and 5. And they want, because notice now there's no function is not necessarily positive here, as is not here. So your functions are not necessarily positive functions anymore. So this is the part that we talked about net change in 5.2. So if you're using this the right endpoint, for example, this one, you would use this as your box. Right endpoint for this one, you would use this as your box. Right endpoint for this one just give you 0. Right endpoint for this one would give you this as your box. And right point here will give you this as its box. So you see sometimes the boxes fall below the x-axis, sometimes the boxes will fall above the x-axis, depending on which one you use. If I use the left, so these are the left endpoint, sorry. If I use the right endpoint for this box would be here, for the first box would be here. The right endpoint for the second box now would be 0. The right endpoint for the third box would be this. The right endpoint for the fourth box would be this. The right endpoint for the fifth box would be this. So you would just use the right end. So left endpoints would use the left value of each interval. Right endpoints would use the right value of each interval. Midpoint now, you'll use a value at the middle. So here would be 0. Here would be -1. Here would be -1 again. Here would be 0 again. Here would be 3. So it's going to be different values for each one. Again, similar to that. Again, it goes to the table of values in number 7, says from 10 to 30, use the table to find the lower and upper estimates of 10 to 30 integral of f of x dx. So you will see that's increasing. So lower estimate would be left endpoint, upper estimate would be the right endpoint. So that's what you want you to do with this one. And then calculate it using, I guess in this case, you can use 1, 2, 3, 4, 5 intervals. So 10 to 14, 14 to 18, 18 to 22, 22 to 26, and 26 to 30. Left endpoints would be 10, at 14, at 18, at 22, and at 26. Right endpoints would be at 14, at 18, at 22, at 26, and at 30. So you, okay. That's how you deal with the tables. Number 19 and 12 says use the midpoint rule with a given value of n to approximate the integral around your answer to the 4 decimal places. So say if we do number yeah, let's do something that's a little bit more involved. Let's do like number 10. So I'm doing midpoint rule for those, and I'm using number 10, which gives me a function with integral from 0 to 1 f of x, which in this case is x cubed plus 1 dx, and they say n that you're using is 5. So if this is my interval 0 to 1, I'm breaking into 5 pieces. So 0.2, 0.4, 0.6, 0.8, and 1. Basically 1 minus 0 over 5, which is 0.2, and then you add that each time. That's your delta x. So this is the process. So b minus a over n. They give you the n and b minus. So the midpoints, that the ones that you're going to be using, the midpoints is going to be 0.1, 0.3, 0.5, 0.7, 0.9. So it's going to be, this integral is going to be approximately f of 0.1 plus f of 0.3 plus f of 0.5 plus f of 0.7 plus f of 0.9, all times the length of each interval, which is 0.2. And f's are now this. You have to plug in that function. So you get square root of 0.1 cubed plus 1 plus square root of 0.3 cube plus 1 plus square root of 0.5 cube plus 1. You get the idea. And all of them at the end, then multiply by 0.2. So you have to use a calculator to do this, but that's the way they want you to approach this. Anything that says use computer algebra system, CAS, or calculators, that's not something you would have to worry about for the test. But if you have some programming in your mind or comfort with using those tools, then by all means practice it. This would be a good opportunity for that practice. Number 17 through 20, it gives you, says express the limit as a definite integral on the given interval. So basically it gives you something that looks like a function with xi's in there, and then it tells you to find what it looks like. So if I do number 18, for example, I get limit as n goes to infinity of sum I equal to 1 to n of, which one is this now? Xi square root of 1 plus xi cube. So this is a right endpoint calculation, delta x, and they tell you that it is from 2 to 5. Basically, your integral is from 2 to 5. Your function is x square root of 1 plus x cube dx. So that's how you would, it's very simple connection there. Okay. So that's how you approach these problems. Again, these are not very difficult problems, but then again, you need to know what the process is to be able to do those. So and they're not uncommon on the test. I have given question like this on the test for that purpose, because it tests your understanding of the concept. Okay, so that's how you operate. Now they refer to theorem 4 for the next set of problems that I want to look at. Let me just confirm that the theorem 4 is what yeah, theorem 4 is basically just doing a limit of Riemann sum using your right endpoint calculations. So we did that like when I was teaching initially, the first video that I did on this topic, I actually did that. But let's just do one of these just to make sure we are familiar with the process. So let's just do number 21. So the integral is from 2 to 5 of 4 minus 2x dx. Well, delta x is going to be 5 minus 2 over n. And the integral is, the summation is going to be limit as n goes to infinity of sum I equal to 1 to n of f of xi delta x, which is going to be limit as n goes to infinity of sum. This is again the right endpoint approximation, writing the limit of sum based on that. Xi is going to be the initial value, which is 2 plus I delta x. So if this is 2, this is 5. Each time you add the delta x to it. So delta x is 3 over n. So it's going to be 2 plus 3i over n. So it's going to be 4 minus 2xi, which in this case is going to be 2 plus 3i over n. And delta x is 3 over n. So this represents your xi. Limit as n goes to infinity, I'm going to comfortably pull out my 3 over n because that is not affected by the summation. I get 4 minus 6i over n. Negative 6i over n, I think I can comfortably pull out the negative as well. 6 over n doesn't get affected by the interval, by summation, sorry. If you remember, I told you guys that the sum of all the values from 1 to n is n times n plus 1 over 2. And this limit, of course, is going to be -9. Now, if I use the method that I learned in this section, in the future section, integral from 2 to 5 of 4 minus 2x, which you should not do it for this problem, because this problem they're asking you to do it using the Riemann method of Riemann sum. But since I have that tool, I can check my answer. And to the root of 4 minus 2x is 4x minus x squared from 2 to 5. It's going to be 4 times 5 minus 5 squared minus 4 times 2 minus 2 squared. 20 minus 25 minus 8 minus 4. -5 minus 4, which is -9. So I did it correctly at the correct answer. Same problem. If I wanted to do this using graphical approach, this is a 4 minus 2x. Looks like this line. At 0, it's 4, and then it has a slope -2, and it goes down. And then from here to 5, four minus 2x, if y is equal to 4 minus 2x, y at x equal to 5, y is equal to 4 minus 10, which is -6, sorry. So this is -6, this is 3. And the area is going to be area of a right triangle, which is 1/2 3 times 6, which is 1/2 18, which is 9. Because it's below the x-axis, the integral would actually be negative of that, which is negative. So 3 different ways to get the same result. But of course, the problem wanted you to use the summation method for this one. So that's how you were to do this problem. Number 29 and 30, they tell you to write the integral as a limit of the Riemann sum. So that's basically what we've been doing and what we did here. So just basically I continued, but you're stopping. Once you write as a limit of the Riemann sum and you simplify it, then you stop there. You don't have to actually do the calculation. So you have to remove all the x's from your expression and delta x. There should be no x or delta x in your expression. It should be all numbers I and n. But once you get to that level, then you can say you have answered the question. The rest of the question, I feel like it's good for you to practice and read the question and so forth. Number 35, and let me stop sharing here. Number 35 through 40, it says, evaluate the integral by interpreting it as in terms of areas. That's just like what I did in my last slide. I drew the graph. I figured out what area does it represent. And I said, this is the area under the curve or above the curve or whatever. And that's how I calculate the integral by interpreting it in terms of area. Problems 41 through, I'd say, 49 plays with the properties of integrals that I told you guys. How to split an integral between two things. What's an integral at a point like 41? What happens if I integrate from 1 to 1? What happens if I have an integral from 0 to pi? What's an integral from pi to 0? Those kind of questions. So it's just kind of like reiterating the properties of integral, but with actual concrete examples. So you can play with those. Problem 55 through 58, it says use properties of integral to verify the inequality without evaluating the integral. Those are the ones that says if the function is, for example, positive from 0 to 4, which is the case here, then the integral would be positive. So just verify x squared minus 4x plus 4 is greater than or equal to 0. So its integral from 0 to 4 would also have to be greater than or equal to 0. And then you can say if this function is smaller than this function, its integral is less than that integral. So that's another property. And again, all of those, you have to now find two things that this function falls in between, which is 1 and √2, and then say, okay, then the integral from -1 to 1 would be between 2 times 1 and 2 times √2. So in a way, they want you to use an approximation for that one. The lowercase m, capital M1 that we were talking about here is that one. So number 57 refers to that one. And I'll let you guys think about 58. It's a little bit more involved, but still very along the same line. It says use property 8 to estimate the value of the integral. Property 8, if you guys, or property 8. Property 8, if you guys remember, was the lowercase m and uppercase m1, the one I just mentioned. So basically, you want to find the lower and upper bounds for x cubed or 1 over 1 plus x plus 4 and so forth, and says the length of the interval times the lowest value is the lower bound. The length of the interval, which is 3 times the higher value, is the upper bound. So that's how you do those. So just have to find the minimum and maximum value of each function over that interval, and then multiply it by the length of the interval. And same thing with the inequalities here. You're trying to compare it with something and say it's greater than this number or less than this number by comparison. Some of this can be a little bit tricky, but again, as I said, give it a shot and see if you can figure out how to compare it with what specific function or what specific value are you going to compare. One of the very important properties here that you can see, there's actually two things that I didn't explicitly say it in my in the past lectures, and those two things are very, very important, and they involve the concept of we know how addition of integrals, additional functions, subtraction functions, scalar multiplier functions work inside integrals. In fact, let me remind you guys of that. If I have integral of fx plus gx is integral fx plus integral gx. So we already talked about this. And the difference would be minus. And if I have a to b k fx, k can come out. So those are all good. These are properties that we have, but there are properties that we do not have, and you cannot use it. So this is probably very important note here. Integral from a to b of f of x times g of x. You cannot, it's not necessarily equal to integral from a to b of f of x times integral from a to b of g of x. You can basically come up with any function example and see that that's not true. Same goes for division, as most of the times they do with multiplication, division, or similar non-properties. So this is not equal to integral from a to b of f of x over integral from a to b of g of x. And also integral from a to b of absolute value of f of x is not only, it's not equal, we actually have an inequality, but it's less than or equal to integral, I'm sorry, greater than equal to, sorry, I don't know, greater than equal to integral from a to b of f of x dx in absolute value. In a way, the way I made help you realize this is, if I have -2 plus 3 minus 4 plus 5, if I have those numbers, if I just add them together, I get 8 minus 5 minus 6, which is 2. That would be this. And if I take absolute value of that, it will be just 2. But if I first take absolute value of each one of them, then I get 2 plus 3 plus 4 plus 5, which is 14. So if I take the absolute value first, then add them all up together, I get a bigger number than if I just add them up, because there's a chance of cancellation, right? Then take the absolute value of the whole thing. So that's what towards the end of the section homework is trying to tell you, that you cannot set the two equal to each other. Number 70, that if you have an absolute value after taking the integral, it's actually a smaller value than if I take the integral of the absolute values. So, and it tells you a method of how to prove that, which I hope you guys can play with that. Okay, so that's yet another nice property or non-property that you guys should know. Now, in section of 5.3 of your book, if you look at it, most of the things goes back to the previous section of calculating, evaluating, but it's now tries to play with the function gx. Remember, gx was the one that we had, which was integral of f of x from 0 to, or from a to x. So it just tries to see if you can understand what gx is by calculating the integrals for different values of x and setting g equal to that. So that's again just playing with the concept of the new function we have learned in fundamental theorem calculus part 1, which is created by a continuous function f. But then problem 17 through 18, 7 through 18 is really where the mechanical steps kick in, which says that you're calculating, and I did several examples like this, you're trying to find the derivative using the fundamental theorem calculus and how the integration and differentiation cancel out. So we have done homework problems like this in the lecture notes, so I think you should be able to do this. If I see any questions on Canvas about any specific one of these that you want me to look at, I'll be happy to go through that one. But as I say, it's very similar. I've done a complete list of different types of problems like this in a couple lectures ago when I was talking about fundamental theorem calculus. Problems 19 through 44 now is fundamental theorem calculus part 2. Basically, you have to remember how to find the antiderivative of each one of these and then evaluate them at the upper point minus the lower point. So that's what you're going to be doing for those problems. So as I said, again, this is very similar to what I've done in the lecture, but if there are some issues with any of those problems, again, please post them on Canvas and I'll be happy to do that. So again, that's basically the big part of section 5.3, that can you do those mechanical steps. After that, as I said, a lot of those things become more of like a conceptual questions that will get like 59 through 63 is now has upper and lower or both functions that you have to worry about and such. So I can in a different video, if there are enough requests of different questions on this section, I can do those ones. But I hope this gets you started through the homework. And if you have any, again, additional question to this, feel free to ask me on Canvas and I will post those videos for those and post them up for you, or come to my office hours. Thank you.